Hello everyone, welcome to Algebra classes. Myself Vasu Chaudhary and today we are going to study ring theory in this lecture. So our first topic is what is ring? So a ring is an algebraic structure R plus dot where R is a non-empty set and plus and dot are two binary operations on R. So this R is said to be ring if it satisfies these three properties where R positive is an abelian group, R dot is a semi-group and these are distributive laws. So before knowing about ring, first we know what is an algebraic structure. So what is algebraic structure? So algebraic structure is a set plus operation or operations plus rules. So if any set have any operation and it satisfies some law, then it is known as algebraic structure. So there is a one algebraic structure I hope you all read about earlier, which is our group. So group is a algebraic structure did be studied earlier in your earlier semesters. So what is group? A group is a set, non-empty set G, where our dot is a binary operation on G. So here G is a set, dot is a binary operation, and the rules that it obeys are your closure, associative, identity, and inverse. So a set with a binary operation and that satisfies this law is known as group. In the same way, a ring is also an algebraic structure. Here our set is R and it has two binary operation plus and dot, and the set of rules it follows are these. First, second one and the third one. So your first law is R positive is an abelian group is as same as of group. The only difference is it is abelian, and we know that a group is abelian if it is commutative. The second one is R dot is a semi-group. So what is semi-group? Semi-group is just nothing if it satisfies the above two properties of a group, that is our closure and associative. That is known as semi-group. And the third are two distribution laws. So if set R, if it is an abelian group with respect to plus operation, and if it is semi-group with respect to dot operation, then it is known as a ring. And also if satisfy these distributive laws. So in order to become any set ring, he should satisfy these three properties. Now in order to get more clarity, I will give you an example. For example, z plus dot, that is the set of integers under the binary operation plus and multiplication, usual addition and multiplication. So in order to z to become a ring, z positive is an abelian group, your z dot is a semi-group, and for all a comma b comma c belongs to z, your a into b plus c is equals to ac plus ab plus ac, and your b plus c is equals to ba plus c. So let us show the first one. So we know from the group that Z is closer, as for all a comma b belongs to Z, your a plus b also belongs to Z, so Z is closer. Here we prove Z plus 2b abelian group. So our first one is Z is closer, second one Z is associative. So for all a comma b comma c belongs to Z, we know that a plus b plus c is equals to a plus b plus c, hence your Z is associative. Third one is identity. Since 0 belongs to Z, so for all a belongs to Z, 0 plus a is equals to a plus 0 is equals to a. Therefore your 0 act as identity, hence identity exists for Z positive. Fourth is our inverse. Since for all a belongs to Z, there exists minus a belongs to Z, such that a plus minus a is equals to 0. That is our E, or minus a plus a is equals to 0. Hence ident inverse also exists for Z positive dot. And the fifth one is our commutative. So for all a comma b belongs to Z, we know that a plus b is equals to b plus a, as commutative is obeyed under the integers. Hence our Z plus dot is an abelian group. This is our first rule. Now the second rule we have to prove is Z dot, here Z plus is an abelian group, and we have to prove Z dot is a semi group. So our first one is closure. So for all a comma b belongs to Z, we know that a dot b is equals to any other integer c that also belongs to Z. So that dot is a closure. And the second one is associative. It is directly inherited from our Z, as integers under multiplication are associative. That is your a comma b comma c belongs to Z, or a into bc is equals to abc. So this implies Z dot to be a semi group. Now the only property we have to show is distributive. That is your a into b plus c is equals to ab dot ac. Since b comma c belongs to Z, therefore b plus c also belongs to Z. So a into b plus c usually exists. Also it is closure under multiplication. So a into b plus c is equals to ab plus ac. Hence your distributive law also obeys. So guys, B is proof that Z positive is an abelian group. Z dot is a semi group, and distributive laws also obey. Therefore your Z positive dot is a ring. So guys, our second topic is special types of ring. So in this topic we are going to study about 5 different types of ring. So starting with the first type. So our first type is ring with unity. So we know about ring earlier. That is our ring. In ring R positive is an abelian. So in all these special types of ring, we don't study about R positive, we study about R dot is a semi group. So few changes are adding in R positive and our ring will convert into a special type of ring. Let me show you how. For example, if the R positive group also contains, R dot group also contain unity or identity, which is the same thing, then this become your ring with unity. Student, don't get confused. In ring we have two type of unity. Let me tell you one and two. One is additive identity and the second one is your multiplicative identity, which we also called unity. So additive identity is for the R positive and multiplicative identity is for R dot. So in a usual ring we only have additive identity. So ring with unity, we can also say that if any ring have multiplicative identity, then it is called ring with unity. So if R dot also obey your identity law under the dot operation, then we said that this ring is a ring with unity. Let me give you an example. For example, your M2Z, that is your set of matrices, set of 2 cross 2 matrices over Z. So we know that any set of 2 cross 2 matrix over integer is a group. Moreover, we can also say that it is an abelian group. So we don't need to prove that M2Z is a abelian group. We also know it earlier. We also know that M2Z is a semi group under multiplication. This is for usual addition and this is for our usual multiplication that we use in matrices. Now the third thing is unity. So we know that let us take a special matrix 1 0 0 1. Since this belongs to M2Z, so for all A belongs to your M2Z, A into 1 0 0 1 is equals to 1 0 0 1 A is equals to A. So therefore M2Z contain identity. So here M2Z is a ring with unity as it contain unity. In ring with unity, it is not necessary that it should contain its inverse or not. For example, in this M2Z, if we take any A and any other B, it is not necessary that B get the inverse of A. I mean, here B act as a A inverse, or we can take like that A dot A is equals to 1 0 0 1. It is not. So student, in ring with unity, it is surety that R positive is an abelian group, R dot is a semi group, and it also has unity. So student, second special type is division ring. This is also a special ring. As I told you earlier, we have to only work on R dot operation, because if it is a ring, as we told earlier, this means that R positive is an abelian group already and R dot is a semi group. So only additions are done in R positive. So if R dot have inverse as well as identity or unity, then that ring is called division ring. Student, for this I have a very famous example, your H that be known as Hamilton's quatrains. What is that? So H is equals to A plus B iota plus Cj plus Dk, where all your A, B, C and D belongs to R, and I, J, J, K, K, I is equals to I, J, K is equals to -1. So student, we have to prove this to be a division ring. So we can easily prove. In order to prove this a division ring, first we have to prove that H positive is an abelian group, H dot to be a semi group distributive as well is must obey, and in order to become it a division ring, the two things, that is your identity and inverse as well. So student, let's do this question. So for R positive, let x comma y belongs to H, that is your x and y might look like a plus b I plus c j plus dk, and x is equals to like e plus fi mj rk. Then your x plus y is equals to a plus e b plus fi c plus mj plus d plus rk. Since your A, B, C, D, E, F, M, J, R all belongs to R, their sum, that is your A plus, therefore they all belongs to R, hence our x plus y also belongs to H. Student, our second property is associative. So let's take any x, y, z belongs to H, then our x plus y plus z is equals to x plus y plus z. Usually the same operations are followed in this usual addition, and that's why it is associative. I have to write, since usual addition operations are followed, therefore it is your associative. Student, our third property is identity. Since 0, we write 0 as 0 plus 0 I plus 0 j plus 0 k, as 0 belongs to R, which is usual. Therefore for any x belongs to H, your x plus 0 is equals to 0 plus x equal x. So therefore identity also exists in H. Your fourth one is inverse. So student, we know that for any x belongs to H, that is a plus bi plus cj plus dk, we know that there exists minus x belongs to H as minus a minus bi minus cj minus dk. This is because for a comma b comma c comma d belongs to R, there exists minus a minus b minus c minus d belongs to R. So on adding, we get a plus bi plus cj plus dk minus is equals to 0. So hence inverse also exists. Student, our fifth property is commutative. That is for x comma y comma z belongs to H. Sorry, we only need x comma y. X comma y is equals to y comma x, which we can easily show by taking again x equal a plus bi plus cj plus dk and e plus fi gj plus mk. Since the operation is usual addition, so we know that your x comma y is equals to y comma x, so it is commutative also. Student, now the second rule is your h dot to be a semi group. So we have to prove two things, your closure and your associative. So let's go to closure. So take any x comma y belongs to h, that is x equal so your xy is equals to so student, after solving these equation we get this. This also belongs to your h, hence your xy belongs to h. We solve this normal multiplication by use our given Hamilton relation, that ij j k k I or I j k equal -1. So you can easily solve that. So your closure is also satisfied. Students, secondly we have to prove associativity for h dot. Student, this is a bit different. In order to prove associativity, we have to know this thing, that your quaternion multiplication is constructed from matrix representation, that is your a plus bi plus cj plus dk can be written as your a minus b minus c minus d b c d a minus dc dA minus b minus cp. And we know that matrix are associative, therefore we can easily say that associativity holds for h dot. So student, we till now prove that your h dot is a semi group. Earlier we also proved h plus to be a abelian group. Now student, let us look at distributive. Take any p comma q comma r belongs to h. P plus q into r is equals to pr plus qr, and r into p plus q is equals to rp plus rq. As we know that associativity under multiplication and dot easily hold, so the distributive law must obey. Now student, since we are proving it to be a division ring, so in order to become a division ring, two special things are required, that is your identity and your inverse. So student, take 1 equal 1 plus 0 y 0 z 0 k. So this act as a identity, that is for any x belongs to your h, 1 dot x equal x dot 1 equal x. So student, identity also exists in h, and for inverse we have to prove that for any q belongs to h, there exists q inverse such that q into q inverse is equals to your 1, because 1 is identity in h. So student, take q is equals to a plus bi plus cj plus k. Then your q bar is equals to a minus bi minus cj minus k. So your q into q bar is equals to a square plus b square plus c square plus d square. This is greater than your equals to greater than 0, it can't be your 0. So student, we know that inverse only exists for non-zero element. So to get q inverse, we get your q bar upon square plus b square plus c square plus d square. Now student, q into q inverse is equals to, it's your q into q bar upon a square plus b square plus c square plus d square. So this q into q bar upon a square plus b square plus c square plus d square, and this is your a square b square c square d square by a square b square c square d square is equals to 1. Hence your inverse also exists. So student, we have proved all the qualities or all the properties that we need to prove your H to be a division ring. That is, H is a ring, and H positive dot is a ring, and it is also have unity and inverse. Therefore your H plus dot is a division ring. So student, our third special type of ring is commutative ring. Student, in this ring, your R positive have this commutative property also. But it is not necessary that it have your identity and inverse. I mean, not necessary, it can be in, but not necessary. The required condition is your commutative property. A very beautiful example of this is your 2e or 2z. So student, this is your set of even integers. That is 2z equals to 2k, where k belongs to z. Student, we know that 2z is a abelian group. No need to prove that from previous results. Also 2z is a semi group for your multiplication operation. This is for under addition. So the third only remaining property we need to prove that is commutative. So student, take any a comma b belongs to 2z, then your ab is equals to your take a equal to k1 and b equal to k2, where your k1 k2 belongs to z. So 2k1 to k2 is equals to your 4k1 k2, and your b dot a is equals to 2 into k2 into 2 into k1. This is also equals to 4k1 k2, because under normal multiplication your elements are in integers are associative, so we can rearrange them as k1 k2 is equals to k2 k1. That's why we are able to write it. So ab is equals to b dot a. Hence here your e or 2z is commutative also. But a student, as I told you earlier also, it is not necessary that it contain your identity or inverse. For example, in 2z there does not exist any a belongs to 2z such that for all x belongs to 2z, your x into a is equals to a into x is equals to a, like this. I mean, there does not belongs to any a. So 2z do not have your identity. So recall what we studied till now. We studied 3 types of ring. Your ring with unity, and second your division ring, and your third one is your commutative ring. A student, ring with unity only contains E. This contains E plus inverse, and this is only commutative. So we are left with 2 more types of ring. The fourth one is your commutative ring with unity. Student, as the name suggested, this ring is commutative plus unity as well. That is your commutative property plus identity. And by saying, every time I say identity here, I mean multiplicative identity. I mean that works under your multiplication operation. So any good example of this is your z plus dot. As in beginning, I prove this to be a ring, and also 1 belongs to z such that for all a belongs to z, a dot 1 equal 1 dot is equals to 1. Hence it has unity as well. Also for all a comma b belongs to z, a dot b is equals to b dot a, as under the multiplication operation commutative property obeys. Therefore your z plus dot is a commutative ring with unity. Since it is ring and it also have unity and it follow the commutative property. So student, this is your last type of ring that I'm gonna tell you. This is your commutative division ring. I think most of you now understand that what this ring is about. It must be commutative, and also from division ring we know that it should have inverse as well as multiplicative identity. So student, any ring that has inverse, multiplicative identity and also obey commutativity is known as commutative division ring. Student, this ring is also known as your field. I mean, in any for any set to become a field, let us take any R. Your R positive is an abelian group. Also R dot is an abelian group. So this means if any ring follow these 1, 2 and 3 other properties, it became a field. So let me give you few other examples. Student, Q plus dot and real number addition, these are the 2 examples that are your field, or we can say commutative division ring, as we know that your rationals and your reals are commutative under usual multiplication and addition. Also 1 belongs to both of them, so that means identity also exists, and also inverse also exists. I mean, for any a belongs to q, there exists b belongs to q such that a dot b is equals to 1, that is b equals to 1 by a, and since it is irrational, so therefore 1 by b belongs to q. Same for real as well. For any a belongs to q, there exists b belongs to b belongs to r, there exists b belongs to r such that your a dot b is equals to 1, that is v equal 1 by a, and it belongs to real number. So this means that these rings have identity, inverses, and also commutative in nature under the usual addition and multiplication. Hence we can say that these are your example of commutative division ring or filled.